Hi, today you're gonna learn how I made my Python compiler 50% faster and cut the binary size in two. So I'm making a Python compiler because most of the compilers make you wait for hours, don't produce the output your user can run. Boring, useless. So I made a compiler that kind of works, but it still generates not that fast. If you include everything, it's like a minute wait. So that's not great. So today I want to explore a topic of how to make it generate less code and make it compile faster. Here you go, very simple program. A equals 5, A plus 3. It translates to something like that. You don't need to really understand it yet. But look, what is this? There's operations like push, pop, pop, pop. Well, essentially, you can think about those operations like that. I have, like a stack, just a bunch of numbers or a bunch of objects, and I can put them on top of the stack or take them from the top of the stack. Very simple. And the big point is, I always know that here, this pop will always return me the value of this push, and this pop will always return the value of this push. So I can know statically which values correspond to which places, right? So I can simplify this. Since this always refers to this, I can just say, hey, save it to the data 0 and just take it from there. And here the same, just save two things in a stack and just use them. So simple. So let me demonstrate to you how the push and pop works. We have two numbers, right? From the example, you push 5, you have 5 in there. Then you pop it, you save it to A. Now the stack is empty. Then you get the A, push the 3, then pop them both and add them and push them. So very, very simple. Example, just like a stack of plates, dinner plates. So the optimization is, instead of doing all those dynamic pushes and pops, you have to calculate what's the length, the current length of the stack. And then I need to add something to that. Then I need to put something somewhere. Just calculate all the indices statically. All right, I've done it. My compiler was doing dynamic stack allocation, stack things. Now it's doing a static one. What are the results? Let's see. The generated C code is reduced by 40%. The binary output size is reduced by 50%. And the C compile time, right? I compile to C, then take it for the C compiler. Reduced by, 30% on average. And the runtime, I get a solid 10% improvement in the program, I've compiled. That's pretty baller. The point is, you would have thought that Python, being a virtual machine and doing all the crazy stuff, the optimization wouldn't do anything. But since you're doing so many pushes and pops and all the stack operations, there are so many of them that they still really actually help you here. Getting solid 10% runtime improvement and 50% size improvement. And of course, you wait much less on the compile time. That's so much better. And, the notes. Of course, this technique by itself did not yield all of those improvements, but it enabled all of the optimizations I was doing, a lot of, if you can see it, right? You can look at here and it's you need to save something in a variable and then only do something with it. But here you can just literally reference the stack slots directly. So it enabled me to not generate a bunch of code I didn't need to generate. Generate less code. Your compile time will be faster. Your output binary will be faster, smaller. That's great. And now, demo time. All right, demo time. So we're Starship and we're landing on Mars. What is gonna happen? Obviously, we're doing the descent. We're air braking. Then, let's see, we're not too far from the ground, so now we're going to do a flip maneuver. And after that, it's going to be the burn to slow us down. So the cool part is, this is run in my compiler. You know, I just compiled and run by the compiler, right? I have a main py, I just run, and here's the program. Very, very cool. So the compiler actually has some value. It compiled it, it ran it. Nice. All right. Till next time. Bye-bye.